In this video, we'll discuss one applications of the blowups that we have seen, which are called tangent cones. And these concern the local study of varieties. And to give you an idea, if we look at this example of this plane curve here, and the point A, which is just the origin, then we can imagine that if we zoomed in on this point, if we get closer and closer, if we enlarge this, then locally around this point, this variety basically looks like just two lines in the plane meeting like this. So locally, if we zoom in, it should look like this. And well, this was just an informal description, but actually we can make this precise using exactly these blowups, which we have seen before. And this is the construction of the tangent cone. So if X is any variety and A is a point in X, then we can always take the blowup at this closed subvariety A of X, and we get this X tilde here. And our first claim is that the exceptional set of this blowup is a projective variety. And the proof is very short, so somehow we just choose any affine neighborhood of this point. Let's say U sits inside some AN, some affine space. And then, well, we get this X tilde by definition just by gluing the part away from A along the complement of A inside U with the blowup of U at the point A. And so if we want to compute this preimage of A, actually we just need to compute what the preimage is here. But then we have by definition that this blowup here is contained in U cross Pn minus 1. And so if we take the preimage of somehow A under this map pi, then this sits inside, well, A cross Pn minus 1. This sits inside here as a closed subset. This here was also closed. And well, this here is just a copy of projective space, Pn minus 1. This is a closed subset here, so it is a projective variety. Okay. And with this in mind, when we have such a projective variety, we have seen that we can take the cone over it. So the set of all vectors such that the class inside the projective space of this vector lies in the closed subset of projective space together with the origin. And so we define CA of X, the tangent cone of X at A, to just be this cone of this pre-image of A under this blowup map. Okay. And the first thing that we observe is that we had this lemma which told us that somehow the blowup doesn't really depend on which exact functions we take at the point. It's only important what the ideal is. And so we did have a well-defined thing here. And then this lemma here shows that CA of X is well-defined, at least as an abstract affine variety. And in the special case when X is actually inside AN and A is equal to 0, then this cone of X, well, this sits inside the cone of the preimage of the preimage of 0 in the blowup of AN. Well, the preimage of 0 in the blowup of AN is all of this Pn minus 1, so it sits inside this cone here, and this cone is all of AN. And so in fact, if you go through this equality here, then you can check that the cone at the origin of this affine variety X actually sits inside the same ambient space. And that was also kind of the example that we had in mind here, because here everything sits inside A2. We look at the origin, and then we get this here. So to make this precise, actually, let's look now at a couple of examples. So we can look at somehow these three curves here. One is basically a parabola, maybe inverted. One is the curve that we had before. And one is this curve that we have also seen a couple of times, this x2 squared minus x1 to the 3. And well, how do we actually calculate in these cases this tangent cone? Well, this blowup of these varieties sits inside the full blowup of A2 at the origin, and it sits inside there just as the strict transform. That's something that we had seen before, just as the strict transform of all of these curves xi. And then, well, what we just do is we take the strict transform, and to get the preimage of 0, 0, we just intersect it with this exceptional set of this blowup here. Okay, And this leads to very fun pictures. These are the pictures here. So for example, here we have x1, this kind of parabola. And then if we take the strict transform, then we get a picture like this, and we see it intersects the so the preimage of the origin is this central line here, which is isomorphic to P1. And here, at least in this picture, this intersects this in a single point. If we look here, this is a bit more interesting. Here, the strict transform gives us a curve like this. And then this central P1 is intersected in two different points. And finally here, in this case, if we look at this picture, then we intersect in a single point. Okay. So now this pre-image pi inverse of 0, 0, this would be this point, these 2 points, and this point here. So these are points in P1. And then if we take the cone again, then, well, a point in P1 corresponds to an entire line in the plane. And so, for example, this point in P1 corresponds to this line. And so this gives us the cone here. And we see, at least in this picture, this is the tangent cone, or this is the tangent line at this parabola at the origin. And here, these 2 points give us these 2 lines here. And they are exactly the lines that we had seen before. And here, this one corresponds to this line here. And so this was just basically pointing at pictures, but now we can also do the calculation explicitly because we have all these nice coordinates for the blowups. And so for this calculation, for example, if we take this x2 and we want to compute its strict transform, well, the x2 tilde, it sits inside in these coordinates. We have the 2 coordinates on A2, and then we have the 2 projective coordinates on P1. And then we get kind of 2 different equations. One is the original equation of x2. This is this one here. And the other is these kind of equations which tell us that, well, basically, I mean, they generalize this relation here that the projective coordinates should be a multiple of the coordinates here. This gave us this equation here. In particular, when the vector x1, x2 is actually non-zero, this equation, you can solve it, and then you get that this vector here is a multiple of the vector x1, x2, as we want. So let's keep this equation here in mind. And then what we do is we take the first equation and multiply by a lambda squared. And why do we do this? Well, then we can kind of substitute, because, for example, we have lambda 1 is equal to, y1 is equal to lambda times x1, y2 is equal to lambda times x2. And then you see we had a square here, and then we can combine the lambda squared times x2 squared to a y2 squared. Similar here. And in the last term, we don't have enough lambdas, sort of. We have 2 lambdas, but 3 x1s. So we can combine 2 of them here, and 1 x1 is left. And we see, I mean, this was some kind of combination of these equations when we are away from this x1, x2 being 0, 0. So this equation here still holds on x2 tilde when you're away from this point. But then we have again seen that if such an algebraic equation holds here on this dense open set, then it also holds on the closure. Okay, and this x2 tilde was defined. Somehow the blowups are always defined as the closure of the stuff that happens away from the center of the blowup. Okay, and so then we have this equation here, and then we want to determine what is now the preimage of this 0, 0. So what happens when we plug in x1 equals 0 and x2 equals 0 in this equation? Well, then we see this term vanishes. So we're only left with the first 2 terms. And this we can factor like this. And we have already seen such equations here. So this is an equation, homogeneous equation on P1. And its solution set is exactly, well, when y2 is equal to y1, we can scale them to be 1, 1. And if y2 is minus y1, then we can scale them to 1 minus 1. Okay. And this gives us exactly these two things in the pre-image. And this corresponds in this picture to the fact that we get exactly these 2 points here. And these 2 points are exactly, I guess, this one here would be 1, 1, and this one would be 1 minus 1 in this P1 here, the central fiber. Okay. And so we have just calculated this, and then we see that if we take the cone over this, then we take basically, well, the real lines through the origin generated by 1, 1, this is this one, and the one generated by 1 minus 1, this is this one. This justifies, then we see exactly these are the two kind of lines which are sort of tangent to this curve at this point here, and that's why it's called the tangent cone. And one thing that we can see, so somehow this was a rather involved calculation. We had to have this trick of multiplying by the right power of lambda, then recombining the terms. But if you do a couple of these calculations for yourself, what you will see is that actually where we started with this equation here, and then to take the cone at 0, 0, the resulting equation, somehow this term was too high order. And so this meant there was still some kind of x1 left. And then when you set all the xi to be 0, and this term gets killed, and we are just left with these terms. And the important thing about these terms was that it was the terms of lowest order, right? So somehow we multiply by lambda to the lowest order, and then we combine all of these to these new terms yi. And then all the terms which have higher order, they still have some xi left. And then when you set xi to be 0, as you take the pre-image under pi, then these vanish. And so somehow the recipe here actually in the end was rather simple. You just take the terms of lowest degree and set them to 0. And this is not just a coincidence here, but in fact, that's the last thing I want to say, is that there's an exercise. It's one of the exercises also in the script, which gives more details and some hints, but it basically gives you a recipe for computing the tangent cone. And the exercise just says that if you have any ideal inside here, such that the origin is contained in the vanishing locus, then if you want to take the tangent cone at 0 of this affine variety, it's just the affine variety cut out by all these initial terms of the elements of J. And here these initial terms, this is just inside, so J is inside this polynomial ring. So F is just some polynomial. It has some of monomial terms. And there's some which are of lowest degree. So in this case, for example, here the lowest degree that appears is 2. And then you just throw away all of the higher degree terms and just take the sum of the monomial terms of lowest degree. And this is this F initial. And then, yeah, so somehow then we get this this equality here, that the tangent cone is just cut out by these things. And so a priori, it looks like this is a rather complicated thing. You have to go through all the elements in the ideal and take the initial terms. And as it's often the case, unfortunately, it doesn't suffice to just take some generating set and then take the initial terms there. But in one special case, namely when x is just cut out by a single equation, and that was also the case that we had above here, then part of the exercise is to show that then it's true that the tangent cone is just cut out by the initial term of this one generator. So we defined tangent cones to study varieties locally at a point. And then here, this exercise tells us how do you calculate them explicitly.